Hello, am I audible?
Hello, sir.
Hello, okay, am I audible and is my presentation clearly visible?
Oh, yes, sir.
Okay, fine, thank you. Okay, so we will start anyways. Other people who will be joining late or they can just watch the video lecture anytime, which is uploaded on the YouTube channel. And so what we will be doing today is that we'll be studying about chronic penny model and the density of state. And this particular topic will cover most of the things like the Fermi energy, the Fermi levels, the probability of finding an electron, probability function, the density of the states, and the counting the number of electrons. Basically, it all comes from the statistics. So we are going to deal with some statistics today, just a basic level of statistics in order to understand how the electrons occupy the energy levels. So starting with the introduction, that's just the protocol we need to follow. So I'm Shazan Bhatt and I'm currently a direct PhD student at IIT Bombay. And for plan for today is to solve the week 3 assignment of NOC 23 EE99. So that is the plan for today. But what I can see, the questions in that assignment require a little bit of little bit understanding of the basics behind those questions, and that is the fundamental thing that professor wants us to explain. That what are the key fundamentals behind those behind the answer of those questions. So starting with the chronic penny model and density of state, let's just dive straight into this thing. So okay, so you know that if you, let's say, if you take an atom and if you have an electron, just this just the basic picture, you know that the electrostatic potential is given by something like this, which you have studied from the basic electrostatics in 10 plus 2 or 10 plus 1 level. This is basically kq square divided by r. The negative sign is because it's a bound system and there is the concept of work done on the system and work done by the system. Leave that thing. The negative sign here is because it's a bound system. So the electron is bound to the to this positive charge. And what that means is that you can plot this thing here because it's a negative sign and it's inversely proportional to r. So it's an hyperbola, but there's a negative sign here. So you can draw the figure something like this. So this is showing the potential felt by the electron, a test charge under the influence of this positive charge, under the influence of this positive charge. So this is the potential. So this is the potential. So this is for a simple atom, let's say a hydrogen atom, which consists of a nucleus and it has an electron. And what happens is that this potential goes into the Schrodinger equation here, and this Schrodinger equation is solved. Now, how I directly jump to the Schrodinger equation, it is as simple as that because you have the potential. The Schrodinger equation requires only one thing for us to put into to get the wave functions, and that is the potential. You have the potential, you put the potential into the Schrodinger equation, you solve this differential equation. This is just a differential equation which you need to solve in order to get the values of psi of r. Now you might be thinking what this r is. You have to take this r in a spherical coordinate system. So this r will be, let's say you can have actually psi of r theta phi, which is the solution of this Schrodinger equation. And now, how to solve that particular thing is not the it's not compulsory at this stage. But what I am trying to highlight here is that from a simple atomic picture, where you have a nucleus and you have an electron revolving around it, it feels an electrostatic potential given by this thing. And if you have this electrostatic potential, you can put it into the Schrodinger equation, where this is the potential. So once you put this thing into the potential thing, you solve the Schrodinger equation for the wave function. You get the wave function as a function of r, theta, and phi. So this is the solution of the Schrodinger equation. And once you get psi of r, theta, phi, this particular thing actually tells us the address of an electron. That is what you guys have learned in 10 plus 2 about the about the quantum numbers. You might be knowing maybe quantum numbers N, L, M. And you might be knowing about S. Leave S for a minute because spin does not directly come from Schrodinger equation. So you guys know about these quantum numbers and principal quantum number, azimuthal quantum number, magnetic quantum number, just 10 plus 2 level physics. And it turns out that these N, L, and M directly come from this particular solution. When you solve for the psi, you get R theta phi. Actually, this R theta phi is R N L M. So these are just the addresses of electron in the spherical coordinate system. That's it. So what happens is that you get these quantum numbers and you get the address of an electron. You get to know which orbital the electron is in, which orbital the electron is in, and these levels get discretized and you get n equals to 1, n equals to 2, n equals to 3, so on and so forth. And if there is a certain electron, then it's having certain angular momentum. Then there is a quantum number associated with it, which is called as L, which is the azimuthal quantum number. Then there is the magnetic quantum number. Then there is another S, which is the spin. Leave the spin for a minute. But this directly comes from solving the Schrodinger equation. Now this picture you have understood, where potential there are certain levels which get formed in a hydrogen atom, and the energy is given by this thing minus 13.6 divided by n square electron volt. This is the just 10 plus 2 electrostatics you have studied. You might be knowing till now. This where this n is the principal quantum number. And if you just solve the Schrodinger equation, let's say in 1D, which is only considering the r coordinate, then this is the solution you will be getting in terms of the n, where n is an integer, positive integer. It's 1, 2, 3, 4, so on and so forth. And now moving on, now we don't have only one atom and one electron. We are talking about the solids. So let's jump into the solids. So the solid picture is something like this. Let's say we talk about silicon. Silicon, the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p2, and 4s0, something like this. That means these electrons are the valence electrons. These are the outermost orbital electrons, and these particular electrons are tightly bound to the nucleus. So these don't play a major role in the conduction process, which you will see in the upcoming slide, because they are tightly bound to the nucleus. They are closer to the nucleus. But these ones are important for us, particularly these ones. Okay, so this is the actual silicon crystal, which you
Sir,
guys, yeah.
how how Pauli SCF principle does work? Yeah.
Sorry?
How Pauli SCF principle works?
Okay, so let's do one thing. That's a good question, but let's do one thing. I'll have a question answer session by the end of this presentation. Then I'll be handling all of the answers. But I'll tell you the answer of this question. So what you are saying is that, let's say I told you that because you solve the Schrodinger equation, you get psi of r theta phi, which are basically the address of the electron, and you get a discretized energy level in case of a hydrogen atom. So this is n equals to 1, n equals to 2, n equals to 3. Now what you do is that you put an electron. There's an electron in n equals to 1. And hydrogen is a very simplistic atom we have. It has a positive charge and it has an electron. That's it. So the Pauli's exclusion principle will not come into picture, at least here. Now what happens is that if we bring in second electron, then the Pauli's exclusion principle comes into picture, because now these two electrons, if they want to stay in this level, they should have all quantum numbers as different. That means what I'm trying to tell you is that these two electrons cannot have all quantum numbers same as per the Pauli's exclusion principle. That means if the electron has n, l, m, n, l, and m quantum number, it has also spin quantum number. Now, how does the spin quantum number come into picture? That does not come from the Schrodinger equation. That's why I omitted this detail here, because the spin directly comes from something called as Dirac equation. It's a relativistic equation. You don't have to deal with it, and you don't want to understand that thing here because it's a very advanced thing that I don't want to touch here. That's how the spin comes into picture. But once, let's say you have certain value of n, l, and m, let's say n is equivalent to some value, l equals to some value, and m equals to some value. But you know that two fermions or two electrons have different spin if they want to if they want to be in the same level. That means if they want to be in the same level, this electron should have spin of plus 1 by 2 and this electron should have spin of minus 1 by 2. And why does that happen? It has a very deep reason. You don't want I don't want to discuss that here because it's going to take a entire lecture. So let's keep the questions at the end, but that this is the overview of how Pauli's exclusion can come into picture in two electron system particularly. So, but in the hydrogen atom, we don't need to think about the Pauli's exclusion as such. So so what happens is that if we talk about the actual silicon crystal now, which is this is the actual structure of the crystal, which you have solved the previous problems for the diamond structure of the crystal. And now what happens is that there are many atoms. There are atoms. These are the atomic nuclei which are closer to each other in the solid. And a similar picture, these are the potentials formed by those atoms by the same electrostatic attraction and electrostatic repulsion. This is the electrostatic potential formed by the electrons in the vicinity of this nucleus. Similar to this picture. This is the same picture here. This is the same picture for multiple atoms. So now you can extrapolate this thing to this second figure here. What happens is that if you can see that this particular thing if you can see this particular thing, this is the potential because of this nuclei, this is the potential because of this nuclei, so on and so forth. It gets repeating. And you see that these overlapped regions here, these overlapped regions, they cancel out and you don't see them anymore here. And that is why at the ends, there is a higher potential than at the middle of this entire crystal. This is the entire crystal. So that's why if an electron is here, its electron cannot just escape the the solid by its own. It needs to just kind of have energy which is greater than that of this. Okay, let's leave that fact. Let's simply talk about from this picture to this picture. We went into this picture, right? We have this picture here where the like this is the potential U of x, the red one. This potential is formed by the repetitive arrangement of the atoms. So if you have atoms, the nuclei of the atoms, so this is the potential of it, this is the potential of it, this the professor might have talked about. So you get this kind of a profile. And now you know that the spacing between the two atoms is something called as lattice constant, which is a. And that's why you see that this particular axis here is an x-axis, and this L represents the length of the crystal. Okay, you have a length of the crystal in this direction, and you have certain atoms which are repeating, and those atoms are repeating at a. The distance between the two atoms is a. The distance between the two atoms is a, which is the lattice constant. So this is the picture up to this thing. Now what happens? What happens? Let's say now we have this particular picture and this is mapped to this thing here now. So you have the positive charge, you have the potential, and now there comes an electron. Till this point we didn't talk about electron. But now we have the electron in the crystal. The crystal is not devoid of charges. Crystal contains many electrons. Let's talk about only seeing one electron right now, because multiple electrons is going to complicate the picture. Now, if we have the let's say an electron moving in this particular potential, what is it going to feel, and how is it going to look for the electron? Because now we have a positive charge here, here, so on and so forth, and this is repeating positive charges, which is the positive charge of the nucleus, and there's the potential of these things, and the electron is trying to roam around these positive charges. How is it going to roam around these positive charges? And whether it because let's say electron here is feeling the electrostatic potential because of this, and all of these are electron is able to feel the electrostatic potential because of all these charges. Maybe some of the potential might be weaker, some of them might be stronger, but the effect of these nuclei on the electrons is completely visible when you solve this picture. So if you have an electron moving around like here, now it's not under the influence of only single atom, it's under the influence of multiple atoms. So what happens is that there comes the concept of something called as Bloch's theorem. So Bloch was a scientist, he cleverly solved this problem, and he simplified the problem by considering that what happens if we consider this particular scenario, and what happens if we consider an electron here, then can we think that electron other, let's say electron here or here, let's say this is the electron here, and let's say it moved up to some region here, then can we say that these two electrons have the same wave function? Wave function comes from solving the Schrodinger equation of this electron. Wave function is just like if you have an electron, so it's a particle classically. But quantum doesn't believe in the in deterministic thing. This thing is deterministic. It has particular location, it has particular momentum in space. The quantum thing tells us different story. It tells us that this particular electron, it's actually a wave just like this. This is called as probability wave, and the amplitude of it shows the probability of finding the electron in particular region. So this is called as psi square x, more psi square. So this tells you the probability of finding the electrons. Okay, so this curve here, what I have drawn, which I have roughly drawn here, may denote the wave function, but I have roughly drawn here. So this pink curve is here showing where you can maximally find the electron in space. This is what with respect to x. So this axis is x-axis. Okay, so that means this particular electron is having certain wave function. This particular electron is having certain wave function. This particular electron has wave function. Now, as per the Bloch's theorem, the Bloch said that this is more of like a mathematical picture rather than a purely theoretical one. It came from pure mathematics. Uh, Bloch considered that if you have this particular picture, that means these are just repeating units of some kind of potential wells. Just like you previously solved the problem of a finite potential well where you had an electron and you solved the Schrodinger equation and you got a wave function of that, something looked like this, which was the psi x. If you square it, you get the psi square x, which is the probability density of an electron, which is the maximum likelihood of finding an electron. This was for a 1D potential well. Now you have repeating potential wells here. In this direction you have x, and in this direction you have u of x. Now what happens is that he considered that if you have an electron here and then you consider the same electron here, those two electrons will be having same wave function, but the only difference will be that there will be some spatial phase associated with it, which is something called as position dependent phase term. And why does that phase term come into picture? You will get a clear answer in the upcoming slides. What I have tried to basically explain in a very layman sense. How does this phase term come into picture? So this is a position dependent phase. It's not a phase related to the time signal, because you can see this particular wave function. It's something which is space related. It's not a time related thing. Right now we are not considering time at all. So he considered that the wave function at some distance will be equivalent to let's say wave function at x plus a, but with some phase term. That means, what does that mean? What does this mean? This means if you have certain region like this, and if you, let's say, consider this as x equals to 0 and this as x equals to a, and let's say for this is a plus b and this is minus b. For the simplification, let's remove this. It means that if you have an electron here and an electron here, that these two will be having same wave function, except these two will be having same wave function, except that there will be this phase term associated with it. Now, how does this phase term come into picture? There is a very kind of different notions which people have been trying to explain. But some of the you can simply think that if you just mod psi square this particular thing, the psi only does not give you any information about the electron. It is psi square which is basically called as probability of finding the electron. Okay, so the psi is not going to give you any significant information about the electron. You have to compute the psi square always. So since the probability of finding the electrons is same, that means psi r square should be equivalent to psi x plus a square. That means this particular thing should be equal, and it's only possible if there is certain factor here which is equivalent to 1, and that is e to the power this thing. If you mod this term, you get its magnitude as 1, that you know from the basic maths. You have to basically mod square it. You write e to the power 2 I k r. So you mod it, you get the 1. That simply indicates that these probabilities at the two distinct locations should be equal in a repeating crystal unit where the atoms are repeating. That means this particular structure. Okay, so that is the whole fundamental of the Bloch's theorem. And this particular thing, what Bloch said is that it's again the related to the potentials, because the potential is itself repeating. So if you take this particular cell, this particular potential well, and if you move in this direction by some value, let's say a, okay, you get the same potential well again. And if you move it again, you get the same potential well again. So that is what this particular thing is mathematically telling you. Okay, it's telling you that if you translate the potential well to the right hand side or the left hand side, because of the symmetry, you can move it anyways. You will get the same potential back. That is the fundamental aspect of something called as symmetry. That means this potential is symmetric around certain value. It doesn't matter whether you translate the potential in this direction or in this direction, you're going to get the same potential. And that is the fundamental thing why an electron will feel the similar potential, and the wave function and the probability of the finding the electron will be same, except there will be a phase factor associated with it. Now there came another model which is called as Kronig Penny model. What Kronig Penny model did, it took the Bloch's theorem and actually solved the Schrodinger equation for it in order to see what happens for the electron energy inside these potential wells, inside this particular solid structure. Now, what he did is he considered this type of a potential, which is the same, a repeating unit, where you can this particularly comes because of this thing, and this is completely repeating over and over again. Now you have to simplify it using the you cannot there I mean this particular thing which I have shown here and which I am highlighting in red thing. Let me just not confuse you. This particular thing which I have shown in blue, which I have shown in blue, for it you can directly solve the Schrodinger equation, but it becomes a little bit, I should say, difficult to solve the Schrodinger equation directly, because you have to include these curvatures. You have to include these non-linearities and curvatures in the potential equation. What you do, you simplify it using the square wells. That's why you consider the square wells, because for it you know that up to this value the potential is constant U naught, and below this value you know that there is some negative potential because the electron is in a bound system, just like in the hydrogen. And it makes our problem very simpler to consider this particular square potential well. Now what happens is that, let me remove this. What happens is that if you consider this to be the origin of your coordinate system, this particular direction is the potential, this particular direction is the x, which is the crystal direction, which is the dimension of the crystal. So we are talking here about 1D problem only. That means you have a 1D crystal like this, which is this is x direction. Okay, and let's consider the length of the crystal to be L. And now this particular problem can be solved in terms of, again, the considering the Schrodinger equation at each of the potential wells. Now what you guys might be thinking, that do we have to solve the Schrodinger equation here, In all these regions, do we have to solve the Schrodinger equation and the crystal is, let's say, going from minus infinity to plus infinity, then we have to solve infinite number of Schrodinger equation. But the problem gets simplified because of the block. So the because of the block theorem, the problem gets simplified because we don't need to solve the Schrodinger equation in the entire crystal. We just need to solve it in here, and we know what the wave function will be here and here and here and so on and so forth because of the blocks theorem. So that is what this thing will be. The Kronig penny will be solving, and what he does is that let's consider for the first region, let's consider this particular thing to be 0 and this particular to be a. That means this particular width is a, and let's say this is minus b, and let's say this, there is a freedom of choosing these particular variables. You can choose any variable as long as you satisfy the repetition of this potential well. Okay, let's consider this as they have considered. Let's consider it to be a plus b. Okay, or maybe you can consider this B or anything, but it should just satisfy the repetition of this potential well. And now what we have is that for the first region, this is the region first. Okay, that is this region. This U is equivalent to 0. Now you know that this particular thing we are considering the potential here to be in this region to be 0, and this particular potential is at U naught, which is the U naught potential given by this thing. And you know from the potential well theory exactly that if you solve the Schrodinger equation d square psi over dx square plus twice m divided by h bar square, you have E, which is equivalent to 0, E of psi. And you write this thing as d square psi over dx square plus k square of psi equals to 0. It has this particular solution, which is the plane wave solution. Okay, so you know how to solve this particular differential equation. You have been doing it from a couple of weeks now. It's a simple differential equation which has a plane wave solution. And now the unknowns are a and b here. Let's leave them aside for a minute. But you know that now the wave function in this region 1 is given by this thing, where this E is given by the energy, which is h bar square k square by 2m, and it comes directly from this k factor because k square we have put as 2m E over h bar square. So you can write E as h bar square k square divided by 2m. This is the energy associated with some k vector, which is the what the k vector is we'll be talking about in upcoming slides. But let's think about the region 2 right now. Now what happens in region 2? Where is the region 2? This is the region 2, and it's for x less than 0 and greater than minus b. That means it is this particular region. Okay, so it is the region which is between the two nuclei. Okay, you consider one nuclei to be here, other to be here. So this is the region between the two nuclei. That is what the second region is. Now you again write the same Schrodinger equation for region 2, but this time the potential in this particular region is certain value, which is U naught. And that U naught will get reflected here because once you write the Schrodinger equation as d square psi over dx square plus twice m over h bar square, you have U minus E of psi of x equals to 0. This particular thing will be, let's call this particular thing as Q square. Then this particular Q square is equivalent to 2m U minus E divided by h bar square. Since I have used U naught, I will put U naught here. That means U naught minus E is equivalent to h bar square Q square divided by twice m. This is the particular thing what they have, what you have your right now seeing on your screen. So why I have kind of denoted these two wave vectors differently, that will become clear in the upcoming slides, but it is necessary that you follow this particular notation, or maybe whatever the sir has shown you the notation, or whatever you understand in a better way. And this is the particular wave function now in this region. And now again, C and D are certain coefficients which we need to find. And what happens now? How do we solve this particular problem? Because we have only talked about this region. We have now talked about this region. That's it. We are not going to again solve for this region, and so on and so forth. Why? Because now the Bloch's theorem comes into picture. Bloch's theorem as you saw in the previous slides, Bloch's theorem says that if you know the solution in this particular region, if you know the solution in certain region, you can extrapolate it to the other region because of the symmetry of the potential. That wave function will be similar in the other region of space around certain other positive charge, but there will be this particular phase vector associated with it, where this a plus b is the dimension as shown in the potentials. So that is the result coming from the Bloch's theorem. Now that means we don't need to solve in other potential wells. You solved here, that's it. You're going to get the electron wave function and the energy in all of the entire lattice, which is the brilliance comes from the Bloch's theorem basically. And now the hard thing here is to find these A, B, and C, D coefficients. And it's not that hard basically. You have to invoke boundary conditions. And if you just take any of the book on solid state physics or any of the semiconductor physics book, you can easily find how to compute these coefficients. The boundary conditions are that the wave function should be continuous at these particular regions. At x equals to 0 and x equals to a, the wave function and the wave function derivative should be continuous. Why that should be the case? Because you know that the electron cannot just disappear here. It's a notion because it's not a type of an infinite potential well where the electron is just trapped there. Okay. And now why this thing is true, because you have the derivatives in the Schrodinger equation. You don't want the derivatives to blow up. If this thing is not defined at the edge, then entire Schrodinger equation will fall. You won't be able to get the solution. Actually, to be honest, there is one more factor there's one more factor uh, linked with this the why the derivative should be constant. But let me not go into that detail here. But this is the simplistic explanation I can give. It's just the you need some boundary conditions for a differential equation to solve in order to get those coefficients, and these are the boundary conditions. Okay, now when you get those boundary conditions, you what you do is that you have psi in region 1, you have psi in region 2. You what you do is that you find psi in region 1 at x equals to 0, and you find psi in region 2 at x equals to 0, and you find psi in region 2 at x equals to a, psi in region 2 at x equals to a, or whatever the coordinates you have taken. When you do these particular things, you are going to get the values of a, b, c, and d. These are the coefficient values. And what you do is that when you combine those particular boundary conditions along with the solution you are going to get an equation something like this. Now it's a very, I should say, some kind of a crazy equation, but it's very easy to derive at this equation if you just follow the applying the boundary conditions to the wave functions which you have earlier found. Now, what this equation is telling you that you remember this q we defined earlier, this k we defined earlier. This k was equivalent to 2m e divided by no this was equivalent to k square was equal to 2m e divided by h bar square, and this q was equivalent to let me just check. Q was equal to 2m u naught minus e divided by h bar square. Okay, so what this equation is telling you, there is a left hand side, there is a right hand side. And what happens is that you see that this is a kind of equation which you cannot solve directly using any kind of whatever you have studied till now, because it's a kind of equation which is solved something called as graphically. What you do, if you have left hand side and if you have right hand side, you plot the left hand side versus certain some k, and you plot the right hand side. And wherever these two plots intersect, you get the values of the you get the values of the this particular thing. You get basically the values of the energy versus the some particular k value. Okay, and that is how actually you arrive at the dispersion relation, because now you will tell where the energy will come from. The energy is embedded in the q values and the k values. Okay, all you need to do is that you need to open those q and k values and plot them. You can plot, let's say, E versus KA, or you can plot E versus, let's say, Q. It's your choice. But certain notations are followed in different books, and people usually stick to one of the notations. But you can definitely plot any of the relations against either K or against Q. But the important thing about this equation to note is that you should think what is actually what these values are here. You know that A, we represented the dimension, which is this thing. Okay. And B, we represented this as minus B, and this was A plus B. So this particular thing was actually B. Okay. And this A and B is again repeating itself. And now what happens is that this is something called as yeah, exactly what I have written here. This is something called as transcendental equation. Transcendental equation is a mathematical equation. If you have, let's say, x square equals to under root of 2x plus 1 plus e to the power x. Well, you see that, or maybe e to the power x square. You see that there is x on left hand side, there is x on right hand side. And if you want to compute the value of x which will satisfy this equation, which will satisfy this particular equation, you cannot directly compute it because it's an implicit equation. It's an implicit equation. That means it cannot be directly solved. What you have earlier solved in your, let's say, lower grades, let's say 2x plus 1 is equals to 0. This is something called as explicit equation because you directly know that x comes out to be equal to minus 1 by 2, and you put x into this equation again, you get 0. That means this x has satisfied this equation. Now try doing this same thing here. You cannot do the similar thing here because you cannot separate the x here, just like you did here. Now, how we solve this kind of a equation? That is the question. These equations are either solved numerically using something called as Newton-Raphson method. Newton-Raphson. These are the techniques which are right now mostly done on the computer because it is easier for us to kind of solve these kind of equations. Or either you can solve it graphically. Graphically. How can you solve it graphically? If you have x square equals to under root of 2x plus 1 plus e to the power x square. I just took a random equation. I don't know what it is. But how can you solve it graphically is that you plot x square. Plot it. And you plot this thing. I don't know how you're going to plot it, but just plot it. When you plot it, when you plot left hand side, right hand side on the same curve versus x, you get, let's say, let me randomly show, let's say if x square looks something like this, and if this particular thing looks something like, let's say, this is just a rough plot. I don't know how this will look. And wherever this particular thing is going to intersect, that is the solution of these two equations. That is the one of the simplest method how the solution is obtained for such implicit equations. Okay. And the similar thing happens in this particular equation. You have certain relation like this. Now, how does this come? How does this equation come? This is coming directly from it by simplifying certain things, which is actually exactly shown here. If we consider, let's say, if we had these particular potentials, now if we consider these potentials to be delta functions with very thin width, you get in that delta x limit, you get this particular equation where the p is equivalent to q square ba divided by 2. Now you plot this particular left hand side of this equation here, and you plot the right hand side of this equation as x-axis. Oops, no, that it's a mistake. What you do is that you plot left hand side of this equation, which is this thing, over this graph, and you know the right hand side is cos of ka. Okay, this particular thing is here ka. What you do now, it's a similar thing what you did here. Now when you plot this left hand side of this equation, you get a curve which is something like this. This is the just the plotting of sine ka plus cos of capital K equals to just this thing, which is highlighted in the pink. Now when you plot this particular thing, that is just a this is just a cost term, and you know how the cost will look like. It will look something like this, and it will have maximum value of +1 and minimum value of -1. So this particular thing is this particular shown as red region. Okay, so just plotting this, not doing anything else. Okay, so when you plot these two things, now you see the magic happens. You see that there are certain regions where the intersection occurs. You see that there is a region where this intersection happens. There's a region where this particular intersection happens. And basically these two equations will be satisfied. Equality sign is showing that means whatever is on the left hand side, that is going to be on the right hand side. That is what the equality sign is showing. That means all of the allowed values will be only allowed, all of the values which are allowed are only between +1 and -1. These values. You cannot go above +1, you cannot go below -1. Why? Because the cos k on the right hand side can allow values only between +1 and -1. And that means the left hand side should also follow the same thing. So when you do this thing, you get this particular curve. Now what happens? When you move from this curve to this curve, you get these regions where the allowed values are plotted. You get this region where there are allowed values. This is between +1. This is between -1. You cannot, the above values are unallowed. The lower values are not allowed. So you get a band where the values are allowed on this curve. Again, you get a band where the values are allowed. And you see a very intriguing thing here is that now let's say this region here, it's not allowed. This region here, it's not allowed. This entire region, I should say, it's not allowed. It's not allowed. It's not allowed for the equation to have these values. Just simple maths. And now when you just see it very closely, you see that there arises certain bands in this. This is first band, this is second band, this is third band, and this is the fourth band. This is the bands and so on and so forth. And if you just go back to this previous figure, you notice that P was something related to energy because P was related to Q. That means this particular axis is energy axis, this particular axis is K axis, which is the it's something related to momentum, but let's not talk about that. This is the wave vector, and you get a plot which shows that energy is making certain bands at certain values. And that is also happening on the other side, just from the simple maths. These are the allowed values of energy, which satisfies the left hand side and the right hand side of this equation. Okay, now moving forward, what happens? Now, if you just remodify this graph, just modify this graph again, you plot energy over here, you plot Ka over here. The same thing. But now what you do is that you use certain values of Ka. You had cos of Ka. Now you use certain values. Let's say Ka equals to 0, Ka equals to pi, so on and so forth. When you do the same thing, this directly comes from here that there are certain allowed values for certain values of K, and there are certain unallowed values for some values of K. And you get the same picture here where there are certain bands for some values of K, and you see that this particular, the width of this, the extent of this region is increasing. This is the similar as the extent of bands is increasing here. Just notice that. That means it's kind of a, I should say, the bandwidth of these bands is increasing as you go higher and higher in energy. Okay, and that means that means this particular thing is directly reflecting the here. So you have got certain bands which are these bands here, and notice that there is a certain gap between these bands. This gap, and it's the same gap which is actually these particular gaps. So these gaps are unallowed gaps. These are not allowed gaps for the electron to have. That means electron cannot stay here because there is no energy level present here. The only energy level are shown in the red, highlighted red. And as it goes higher and higher and higher, this band increases in width. That means as you go higher and higher energy, there is an entire band of energy is present for the electron to have. And you no longer get these discretized elements of the energy. Okay, so it is like if you have something like this at lower, then you go higher, you get more and more bands, and this is the same thing happening here. So there are many levels present here. It's just like a continuum of energy levels. And they again, and there are few energy levels here, few energy levels here. So as you go higher and higher in energy, these bands become more widely spread. So that simply comes from solving the chronic Penny model. Now, why is it important? Why is it important? It is important because it says that electron cannot have all of the energy values inside the solid crystal. Okay, whenever the electron is in the solid crystal,
Sir,
it is going to,
what is the band system used for?
sorry.
Your example, sir.
Mm-hmm.
So, what is
Yeah.
the band system used for? Uh, any example, sir?
Can you just speak louder? You are not audible clearly. Either your voice is breaking or there is some issue. Yeah, speak. What's your name? Sanjeev.
Yes, sir. What is the use? What
What is the use of?
and some? What is the band system used for? And
Oh, you mean you
some
mean you mean
examples,
what is?
sir. And some examples.
Okay, okay. So I think I partially got your question. You mean what is this band system or band structure used for, right?
Yes, sir.
Okay, so that is what we
Yes,
are
sir.
going to. That's what we are going towards. So I'm just making a firm kind of base so that I can go into that region. I will be talking about where this is used. So this particular thing is the fundamental key aspect of all of the solid state devices or solid state materials. Whether it's metals, semiconductors, whether it's any kind of whether it's any kind of solid state material. Okay, so that's what I will be talking about. Now, what happens is that let's say I showed you here I showed you this thing in particular here, which comes directly from solving these equations using the Kronig penny. You will see in the upcoming slides that these particular regions of the bands, they actually give rise to something called as valence band and conduction band. And how this picture comes from here, that is what I'm going to talk about. These are exactly these particular things which come from solving the solving the chronic penny model, which is basically the solving the Schrodinger equation. And and why this is important is because by understanding this band diagram, you can by understanding this band structure, rather, you can understand how electrons move, how electrons carry current, and if you understand how this happens, you have understood how a device works. That is the simplest example of why this is important in devices. Okay, so that's what we are going to jump to. Okay, so this is let's take a pause here and let's for a moment pause in this particular region and let's try to think about one more explanation for this particular system, how these bands can arise. This is one way of explaining it. Maybe if some of you found it complicated because of the maths involved, let me just briefly give you another theoretical explanation of how the bands can arise inside a device. Okay, let's have a very simple picture. Let's assume a free electron having a plane wave Schrodinger equation solution. That means it's a free electron. It's not under the influence of any potential. It has the solution of Schrodinger equation like this, which comes from solving d square psi by dx square plus k square psi equals to 0. So you get this plane wave solution where the energy is given by h bar square k square over twice m. So an electron has all of the accepted states. There are many. continuous states present over this parabola, which is the energy versus K. So electron can have any of this state. It's a continuous parabola. There is no discretization in this parabola. Okay, so it's a continuous thing. This is for a free particle, not in any potential. Okay, now if an electron is now moving inside a periodic lattice, earlier the electron was free, it was moving. It was not under the influence of any potential. Now the potential is there. Now the electron is moving like a wave because we have considered the solution of the electron to be a plane wave. So the plane wave, let's say, looks like something like this. It's a probability wave here, but let's consider it as a simple wave. But what happens is that if you have electron and if the wavelength, if this is the distance between the two atoms as a, this is the same as this. If you have an electron coming from this side, which is having a wavelength very huge, like this order, let's say this is the wavelength, lambda of electron, and it is much, much greater than a. Okay. So, yeah, Sanjeev, you have a question? Hello.
Not now, sir.
Okay, okay, sure. So let me just finish it, then we will jump to directly to the questions because it's going to take 20 or 30 minutes for solving the questions. That'll be it. Then we can discuss the questions. Okay. So when the electron wave enters the crystal, now what I have shown, let's say if the electron wavelength is much greater than the lattice constant, that means electron wave will look something like this. This is the electron wave. It's the wavelength of the electron. It is as if electron won't feel these atoms at all because it is just traversing these atoms without getting influenced by it. Okay, it is just like if you have certain stones present here, and let's say if you are standing over these stones, let's say if these are the legs of a person and if the other leg is here, let's say he's a some giant person, maybe these are the arms, let's say. Yeah, this let's say this is some weird person, a giant person, and a giant person is trying to get through these stones. This is stones. These are stones, like let's say stone one, stone two, three, and so on and so forth. If a giant person directly puts one foot here and other foot over the, I don't know how many stones, it's not going to matter what is in between. Okay. So similar thing happens for an electron. I mean, it's very weird, but the similar thing happens for an electron. It is if the wavelength of the electron is much greater than the lattice, the distance between the two atoms, then electron is not going to feel any of the potentials as such. Or even if it is going to feel, then overall on an average it's going to move freely inside the lattice. So the electron moves through a lattice like a free particle, but only when only if the k is small. That means wavelength is large, because the k you can write it as 2 pi by lambda. It's in k space. So if the lambda is much much greater than a, that means k is small and lambda is large. Okay, so now what happens if the wavelength is comparable to the lattice constant? So this was for the case when wavelength of electron is much much greater than lattice constant. It is as if the man is just kind of trying to dodge over the stones, and it does not matter how many stones you place here because he's placing one foot here, other foot here. So this is like the wave going through it without any influence. Now, if you consider an electron wave with larger k, that means k equals to 2 pi by lambda. That means lambda is small. How small? It is of the order of lattice constant. That means the distance between the two atoms. Let's say if you have an atom here, another atom here. This is A, then this is also A. Then let's say the electron wave looks something like this. So this is the overall 2A is the wavelength of the electron. Okay. Now, very bizarre thing happens here. You see that in this case, when the electron will try to be kind of electron will try to traverse between these atoms like this, it will get some kind of influence from this nucleus, from this atom. Okay, and maybe because of it, electron will kind of backscatter. It will get reflected, because let's say if you have a positive charge here, electron will try to go. You have another positive charge here, electron will get kind of attracted and it can get reflected in the other direction. Okay, that can arise because electron wavelength is now comparable to the lattice constant. Earlier, it was not able to feel any of the lattices, any of the crystals. Okay, so now what happens is that this is the particular reflected thing, which let's say the electron gets, some of the part of the electron gets reflected. The wave gets reflected basically. So you get something like this, where you have a incoming wave which is going in this direction, you have the reflected wave from the atoms going in this direction. Now, it's a very simple picture, but it gives a very, I should say, satisfying explanation of why the electronic bands arise. Okay, now you know that your wavelength was equivalent to 2 times the lattice constant. That means if you have, let's say, a wave going in this direction and a wave going in this direction like this, you know that if this amplitude, the crust of this interferes with the trough of this, they are going to cancel each other. There will be interference. Interference of what? Electron waves. Okay. It is just like a wave going in this direction. It gets reflected and the wave coming in this direction. And if the phases are in, if there is a phase difference of pi, then these are going to cancel each other and you get a zero, almost negligible, as if the electron has went somewhere else. And what has happened to the electron, that's a different story. But we're talking in terms of a wave picture, clear wave picture here. Okay, so there will be interference of these waves, wave going this side, some of the wave getting reflected this side, and there will be interference. Now, what happens is that if the constructive interference can happen if this wavelength is some integer multiples of let's say 2 pi. That means if this condition is satisfied, that means if, for example, n lambda equals to plus minus 2a, you get a constructive interference. That means you get a wave traveling in this direction, and other part of the wave somehow will be like this, and you get a constructive interference if this condition is satisfied. And this is the same condition what you study, something called as Bragg's condition, which come from the Bragg diffraction technique, and even people can find it experimentally. It was found by these two scientists, Bragg, who I guess won the Nobel Prize. They were son and his father. Both of them were awarded the Nobel Prize for this. And you get constructive interference if the condition of constructive interference is satisfied. That means n lambda is some plus minus 2a, which is the lattice constant. Or in terms of the wave number, you can write it as k equals to plus minus n pi by a, because k is equivalent to 2 pi over lambda. Okay, that means this wave vector is now is not continuous now. It is varying as some integer multiples of pi by a, where n equals to 1, 2, 3, so on and so forth. Earlier in the free particle case, the electron, this k was continuous. This energy was continuous because k was continuous. Now, what is happening? The k is getting discretized, and there are only certain values of k allowed. Why? Because of the interference happening. Electrons going in this direction, some electrons getting reflected, interference of waves gives rise to certain values of the k which are allowed in the system. And these k's are the wave vectors, and they indirectly determine the energy of the electrons. So that is why the electron energy gets discretized. You get those bands now. Okay, so that is the simplest explanation. And let's skip this particular portion here, but this is the explanation what I'm trying to give. Maybe if I will be able to explain this. Okay, okay, up to this part you get a discretized K. Now, now what happens is that if you have some electron wave going this direction. Let's say it can be represented as e to the power I k x, and some electronic wave coming in this direction. This is minus x because x is this direction, and this is minus x direction. And this particular wave going this direction can be written as e to the power I kx. So overall, you can have something called as standing wave when a wave with same frequency is going in this direction and the coming reflected back in this direction, you get something called as standing wave or standing wave pattern or something called as stationary wave. You might be knowing about stationary waves maybe. And this is the particular wave equation, or I should say the way you can represent the waves something like e to the power I k x, where this k is equivalent to n pi by a, and you can write e to the power minus I n pi over ax. If you assume n equals to 1, you get e to the power minus I pi by ax. Plus minus because some part is going here, some part is going here. Okay, now let's remove this thing. Let's keep it here. Oh God, I think the power has gone. There's a power. Oh shit.